Hello and welcome to another session on data mining. Today we'll continue our discussion on various types of machine learning problems other than the binary classification or regression problems. And for that, we are going to talk about today is called one-class classification. It goes by different names. It's also called unary classification or class modeling or novelty detection or abnormality detection or anomaly detection. There are so many different names for a very simple concept. The idea here is that in training, you are given examples of only one class. So let me give you a use case or an example where this would be really useful. Let's say you want to detect whether a person is having any cardiac abnormality at a given time or not. So what you do is you monitor the electrical activity of that person's heart using an electrocardiogram, or let's say you use an Apple Watch or something like that. And what you get is you get data from that person, like this one. So you get a recording of that person, right? In terms of, so this is the time axis, and you monitor their electrical activity, and that's going to appear as beats. So a single beat is going to be this one, right? And you can extract that, then you can move on to the next beat and so on. So your goal is to determine whether the person's heart is functioning normally or abnormally, so you can, let's say, call the authorities if they need help. So the way you can do this is, one way you can do this is that you get a data set and you get it labeled from a doctor. So you get a bunch of abnormal cases, which are going to be your positive examples. You extract features from those, and then you get negative examples and you get features from those, and then you can determine a classifier that discriminates between the two. That is the typical way we would do that if we were to use binary classification, right? So the issue with this is that we would need to get labeled data. We'll need to get labels for all the positive and the negative examples, which can be quite difficult, right? So another approach we can do is we can monitor the electrical activity of the heart, and if anything deviates from that normal behavior, we can flag that as an anomaly and raise an alarm, right? And that's the fundamental idea or the central idea behind one class classification. So in training, your examples are only from one class, say the normal class. And what you are interested in is identifying those examples at test time that differ from the given class. Okay, so let's say you've got a beat over here, because most of the time a person's heart is going to function normally. So let's say you extract those beats, you extract some features from them, you present them in a scatter plot, and then for a given beat, you determine whether that beat lies closer to all the other beats that you already have. And if it does, then it's normal probably, but if it's far away from the normal beats, then we can flag that as abnormal. So that's the fundamental idea behind one class classification. Essentially, what we are interested in is identifying examples that are anomalous, that don't follow the same patterns as the examples of a normal class. And there are different types of classifiers available to do that. The simplest one, of course, is again the nearest neighbor one. Let's say if you got a test example, you don't know whether it's normal or abnormal, but you have all the training examples and you have features of those examples. Let's say you got two features, you've got a feature one here and a feature two here, right? So you represent a given examples in this feature space, and then what you do is you determine the distance of a given example to examples of the target class, which was available during training. Remember, one class classification, or in one class classification, you only have examples of the target class. And that is a single class, not two classes, right? So what you do is you determine the distance of a given example, which is over here, to all the examples in your training set. And if you see that the nearest neighbor of this example, the test example that you have presented, is like small, if that distance is small, the nearest neighbor distance is small, then probably this example is going to follows the same pattern as all the normal examples out there, right? So we can classify that as belonging to the target class. However, if it's far away, then what we can say is that it's probably abnormal. It doesn't belong to the target class. A slightly more formal version of this classifier is what is called the nearest neighbor data descriptor rule. What it does is that for a given example, let's say this example over here, this one, what you do is you determine its nearest neighbor in the training set. So if this green example is a test example, you determine its nearest neighbor and you calculate this distance. Let's call it D, right? Or let's call it D1. And you divide it by the distance of your nearest neighbor example with its nearest neighbor example. So in this case, because this is the nearest example to your test example, you determine its nearest example which is going to be this one in the training set. So let's call this distance d2. And what you do is you take a ratio of d1 over d2. So what's written over here is the same thing, but in a bit more mathematical notation. But I hope this is simpler. So you take a ratio of d1 to d2, and if this ratio is less than 1, you say that this example, this green example, which was given at the test time, belongs to the target class, and if it doesn't, then you can say that it does not belong to that target class. So you can use this, you can threshold this ratio, d1 over d2, whether it's greater than or equal to, whether it's less than or equal to a certain threshold, and you can control how much sensitivity you want by changing this particular threshold over here. So there's a very simple rule. If you want to read more about it, you can take a look at this excellent thesis that talks about these nearest neighbor, one class, with different types of one class classifiers. It's pretty old, but it's still a very useful technique. You can also average the distance of k nearest neighbors, and there are different variants you can get into. There are other types of one-class classifiers available out there as well. One of them is called support vector data descriptor, and it's a very simple classifier. So imagine if you've got examples in the training set, and all of those examples, what you essentially want is you want a curve, or in this case, in the case of this support vector data descriptor case, a sphere around your all the target class examples, so that anything, if a given test example falls within this sphere, then it belongs to the target class. If it doesn't, then we say that it does not belong to the target class and is anomalous. So this is the central idea. What it does is it finds a hypersphere. If it was only in 2D or it was in 3D, we would say that it is a sphere. But if it's in higher dimension, if your feature representations are if you have more than 3 features, we can say that this is a hypersphere. So it finds this hypersphere with a center at A and radius R, so that the targeted class examples lie within the hypersphere. So all the training examples should lie ideally within that hypersphere. But there can be some outliers in your training examples as well, because essentially what you are doing is you're collecting data without labels. So your assumption is that the target class is the representative class or the majority class, and there are only a few examples that will belong to the anomalous class in this case. So if you have collected data and you haven't had it filtered or labeled, this would be a better way of doing one class classification in comparison to what we talked earlier, the nearest neighbor rule, right? So what we do over here is, if you break it down in terms of the representation, evaluation, and optimization principle, what we are looking for is a decision function that classifies a given test example. And in the case of the support vector data descriptor case, our representation is a bit different. What we do is we take the distance of that example from A, which is the center of the sphere that we are looking for, and we subtract it from the radius of that sphere. So what it essentially means is f of x is going to be greater than 0 if this point x lies within the sphere of radius r centered at A, and it's going to be greater than 0 if x lies outside of that sphere. So that is the representation for this particular classifier. Now what we want to do is we want to do evaluation on it. That is, we want to say what qualifies for an error in this case. So you're given a set of training examples. Let's say you've got n training examples. Then what you essentially need is a loss function. We need to define a loss function that measures whether a training example is an error or not. So let's say you've got an example xi in the training set. What you do is you calculate its prediction score, which is essentially f of x, which is given over here. And we know that f of x should be less than 0. That is, this given example, xi, should lie within this sphere. But if it's greater than 0, then probably it's an outlier. Okay, so this then becomes our loss function. If for a given example x, it lies for a given value of a and r, if it lies within that sphere, there is no loss. But if it lies outside, if that training example lies outside of that sphere, then we give it a loss that is proportional to how far away that example is from the center, or how far away is it from the radius, outside the radius of the sphere, right? So we calculate the loss of all the training examples over here, and we also want to make the tightest sphere possible. So the optimization, this is second bit, evaluation bit, has two components. This bit over here tries to force to get a sphere of with center A and radius R that contains all of the training examples, and it measures how many examples actually fit in there and how many examples are actually outside or at and to what degree. So all this is doing is measuring error. So this you can interpret as empirical risk. Okay. And then you also want a minimum radius of that. We want the tightest sphere possible that gives us good results. And this parameter C over here controls the compromise between these two things. Okay. So that's what we achieve by this. This is how support vector data descriptor works. And you can optimize it using any optimization techniques, say stochastic gradient descent or gradient descent or anything else. So if you relate it to our discussion on how different problems can be solved in machine learning, all we need is to change the representation and the evaluation bit. In this particular case, we have chosen a representation that is based on a sphere, whether a particular example fits within the sphere or whether it's outside the sphere, and then we define a loss function that measures for a given training example whether that example lies within the sphere or not. And then we optimize over that. We choose parameters A, which is going to be a vector in the same feature space because it's the center of the sphere, and the radius R, and we try to solve this optimization problem to get a value of A and R. Okay, so the optimization process in this case is going to give us the center location A, and it's going to give us the value of R, which we can go ahead and then use to determine whether a given test example lies within the classifier, lies within this sphere or not. And this can also be kernelized, and there can be so many different variants of this, but that's the central idea. And you can see, what I really want you to understand is not just one class classification over here, but essentially how we change the loss function and how we change the representation to solve different types of machine learning problems here. Okay. And of course, there is a support vector machine to do the same thing. It uses a representation that is much like the representation of a classical support vector machine. So f of x is w transpose x plus b. So the parameters you have are x and b. But we will change the loss function because we are solving a different problem than in comparison to binary classification. We are trying to solve one class classification problems. So what we want is that all examples or the target class examples should have a positive score. So they should lie above a particular line that is determined using W transpose x plus b equal to 0. So all these training examples of the target class should lie above this line. And this line should be as far away from the origin as possible. Or in other words, what we want is that all the outliers in this case are mapped to the origin. So what we want is we want f of 0, which is going to be since f of x is equal to W transpose x plus b, if you put f of 0 in it, you get b. What we want is this b should be less than 0, okay? Because that makes sure that all these other examples should lie at the origin, okay? But we don't have those examples, so we are treating this origin as a proxy for all those outlier examples. And the rule becomes, or the loss function then becomes, that all the examples in the training set should lie above the line, and if they don't, we incur a loss for that particular example. So there is an error whenever a point of the target class produces f of x less than 0. And the other corresponding target or loss is going to be when the origin is producing a score that is greater than 0. So if we combine these two ideas, we come up with a very simple loss function, which is given over here. Now you see that this loss function that is on your screen has two components. It produces a positive value whenever b is positive. Remember, we wanted a negative b because we wanted all the outliers mapped to the origin. So the origin should be below the line, hence b should be negative. But if it is positive, then we incur a positive loss. Similarly, we said that all the training examples should have a f of x that is greater than 0. That is, all of these points should lie above the line. And if they don't lie above the line, we incur a loss. So if f of x for a training example is greater than 0, then it's okay. There is no problem there. There is no error. But if f of x is less than 0, then we have an error. So what this function does is that it measures the loss for all the training examples, for a given training example. And it's going to produce a positive value only if b is positive, that is, the line falls below the origin or the origin falls above the line, or if, so this is the or bit because we have a plus here, or for a given training example, f of x is negative. So there are examples below the line. There are target class examples below the line. And what we do then is simply sum up all the training examples, sum up the losses of all the training examples over here that you can see. And then we have our good old regularization term that is given over here. And the good thing about this is that it can be kernelized as well, and it can lead to really good solutions. So this is one class classification, one class support vector machine that you can go ahead and use. And it's available in different Python packages. All of these classifiers that we talked about, support vector data descriptor, nearest neighbor rules, and this support vector machine are available in Python, so you can go ahead and use them in your applications. But at the same time, what I want you to learn is how do we go from the definition of a problem to designing a representation for that, or a classifier for that, or a machine learning model for that, and defining a loss function. And then we can do the optimization. So if you think about the one class classifier, you have got a representation, which is the same good old f of x is equal to w transpose x plus b. You've got an evaluation bit, which is essentially a loss function over here. Okay, so we defined a loss function. So that is loss definition. And then the third bit is optimization, which you can do using gradient descent or using other tools. Okay, so that's pretty much it. In terms of these different type of classifiers. What we are going to do next is that we are going to try to see how these problems how these classifiers can be useful in solving a practical problem. So let's say we want to do abnormal beat detection. This is something I did quite a lot back during my masters and stuff. So we used abnormal beat detection in ECG to test different type of machine learning models, and we developed one of our own one-class classifiers as well. But if you talk about the problem, then the problem is ECG-based automated detection of abnormal beat has low generalization across individuals. And this is pretty interesting. What it essentially means is that when our hearts are beating normally, let's say my heart or some other person's heart, if we extract ECG patterns from it, they're going to look pretty much similar. And the reason for that is for a given lead, if you've ever taken an electrocardiogram, they hook up a bunch of leads to you. So for a given lead, normal behavior of your heart or for a single beat is going to look something like this. So there's more physiological definitions of what these different up and downs are. So for example, this is called a P wave, this is called a Q wave, this is called an R wave, this is S, and then this is called T waves. So this is what the behavior of a normal heart should look like at a certain lead. Any deviations from that should be can be interpreted as abnormalities. But there's an interesting pattern, and what we see is that if we project all of this beat, a single beat, which is recorded using electrocardiogram into a two-dimensional feature space using, let's say, PCA, we observe patterns like this. So the normal behavior of a given heart lies roughly within the same location. If you look, so it lies over here, right? So you take different beats of a single person. This is a single person. This is another person. You can see that all of these roughly lie at the same location, right? All the normal beats are pretty much tightly clustered. However, the abnormal beats for a given person, which we know because this data set had been labeled by experts, we know that these abnormal beats, which are shown in blue over here, are different, lie at different locations for different people. And that makes sense if you think about it, because whenever there is an abnormality in the heart of a person, a different person may have a different type of abnormality as well. And that is reflected in these plots. So what this means is that probably it's very difficult to generalize across different types of people uh, because their abnormalities are going to be very different. So what we can use then is we can use one class classification trained over normal beat data, and we can then detect abnormal beats for a given person, much like what an Apple Watch does these days. Okay, so that is the goal. So we want to train classifiers, one class classifiers on the normal beats of each individual. And we did that. We tried with different classifiers. In terms of this particular data set, we had about 73,000 normal beats from different individuals. And then we had a bunch of different type of abnormal beats. So these are different types of abnormalities, whether there is a blockage in the left part or the right part or so on. Okay, so we had different types of abnormal beats. And what we wanted to see is whether we can use one class classifiers or how do these perform. So what we did is we did some pre-processing, we extracted some features, and then we extracted it, gave it to a classifier. Remember, in this problem, the example is a single beat. So what you do essentially in the pre-processing bit is you separate out from this time series data or this simple electrocardiogram recording individual beats. Where does a beat start and where does it end? So we extract data like this. Okay? So you separate out these different types of beats. Once you get that, we extract some features and then use one class classifiers. And remember, there's another point here that's quite subtle. Ideally, I shouldn't be dividing the data of a single person in train and test, right? So if I use a person for training, I shouldn't be using the same person for test. But in this case, since we are doing one class classifiers or person specific one class classifiers, that's okay to do. I want you to see how good or bad that a given machine learning model is in detecting abnormalities for a single person. We used AUC score for this, and then we used one class SVM support vector data descriptor. This is a linear programming data descriptor, which is another model for doing one class classification. The K nearest neighbor data descriptor, and this is something that we developed. It's called quadratic programming data descriptors. And we saw what is the AUC ROC score, which is plotted on the y-axis over here for different volumes of training data. So if you use 50 beats in training, this is the AUC ROC you get for beat classification, average across all persons for different types of machine learning models. And we can see that the best one, surprisingly, is actually the K nearest neighbor data descriptor. Similarly, however, if we increase the amount of data, then we can see that these at, let's say, 100 beats, if we use 100 beats of each individual for training, we can see that one class SVM actually performs or gives you a better prediction accuracy in this case. If we choose our beats randomly rather than using the starting n beats for training, you get a slightly different picture, but pretty much the same thing. So that is how you can use these classifiers in practice for detecting cardiac abnormalities. There are two things I want you to understand in the context of one class classifiers. Our goal, although, was to learn one class classifiers, but there was a bigger goal here. That is, how do we go from defining a problem to defining a representation and an evaluation for that, so that we can solve other types of machine learning problems. So I hope you had fun with this. Please go ahead and try wherever you see a possibility of using these classifiers. These are really, really interesting. You only need unlabeled data, and you can detect anomalies using these. Okay, thank you.